So combined gas law, it combines Boyle's law, Charles' law. So P1 V1 over T1 equals P2 V2 over T2. So you kind of see the relationship still. Pressure and volume are indirectly proportional. Volume and temperature are directly proportional. So then also pressure and temperature are directly proportional. So everything with the ones, so P1, V1, and T1, those are considered the initial pressure, volume, and temperature. P2, V2, T2, those are the final pressure, volumes, and temperatures. The units need to be consistent, and your temperatures need to be in Kelvin. So a weather balloon has a volume of 525 liters at ground level, where the temperature is 294 Kelvin and the pressure 749 millimeters of mercury. What would be the volume of the pressure of the balloon? When it reaches an altitude where the temperature is 244 Kelvin and the pressure is 247 millimeters of mercury. So you got to list your knowns and unknowns. So V1 is 525 liters. T1 is 294 Kelvin. P1 is 749 millimeters of mercury. V2 is my unknown. My temperature 2 is 244 Kelvin. My P2 is 547 millimeters of mercury. So P1 V1 over P1 V1 over T1 equals P2 V2 over T2. And then you have to rearrange to solve for V2. So P1 V1 T2 equals T1 P2 V2. I just cross multiplied. And then I will divide both sides by T1 P2. Now I'm just going to plug in my numbers. So 749 times 525 times 244 divided by 294 times 547. That will be my V2. So because of the multiplying and dividing, it is best for you to group your numerator and your denominator in their own parentheses. So 749 times 525 times 244, close parentheses, divided by open parentheses, 294 times 547, close parentheses. You end up with 596.6179, etc. So if I look at all my numbers, at least the number with the least amount of sig figs is 3, so it's going to be 3 sig figs. So 596.6 becomes 597 liters. It's a weather balloon that's a pretty big balloon. That's why the number is very big. So list your knowns and unknowns, your formula, and also plug in your numbers, and then give your answer to the correct amount of significant figures. Don't forget your units. 500 liters of a gas in a flexible walled container are prepared at 700 millimeters of mercury at 200 degrees Celsius. The gas is placed into a tank under a high pressure. When the tank cools down to 20 degrees Celsius, the pressure of the gas is now 30.0 atmospheres. What is the volume of the gas? So notice how the units are not the same. So these have to be the same. Your temperature needs to be in kelvins. So let's see. We have a volume of 500 liters. We have a pressure P1 at 700 millimeters of mercury. And then my temperature is 200 degrees Celsius. I have a new temperature of 20 degrees Celsius. I have a pressure of 30 atm. What is my V2? So I'm going to do the following. I will convert this over to Kelvin. So this is 473 Kelvin. This is going to be 293 Kelvin. I will make both my pressures in atmospheres. So I will divide this by 760 to make it atm. So 0.921 atm. So P1 V1 over T1 equals P2 V2 over T2. I am solving for V2 again. So 0.921 times 500 times temperature 293 divided by 473 times 30.0, that's going to equal V2. So let me see. Calculator. Here we go. So 0.921 times 500 times 293, close parentheses, divided by open parentheses, 473 times 30.0. I end up with 9.5085. So looks like we have 3 sig figs for at least number of sig figs. So this becomes 9.51 liters. Ideal gas law, PV equals nRT. P stands for pressure, it must be in atmospheres. V stands for volume, must be in liters. T is temperature, must be in kelvins. N is the number of moles. This is related to the ideal gas law constant. R has a value of 0.08206, and the units are liter atmospheres over mole Kelvin. So whenever you're using this law, you're going to have to make sure your units are correct. So if you need to convert, you need to convert it. What is the volume of 110 grams of CO2 at 273 Kelvin and 1 atm? So we're trying to find a volume. We are given a temperature, 273 Kelvin. We're given a pressure at 1.00 atmospheres. We're trying to solve for volume. We're kind of given moles because moles is going to be the 110 grams divided by the molar mass of CO2, which is 44.01. That will give me my moles. Let's see what that is really quick. So 110 divided by 44.01. So about 2.499-ish moles. So PV equals nRT. R is going to be given to you. It's not going to be the question. You just have to know when to use it. So volume is going to be nRT divided both sides by P. So the volume is the number of moles. So approximately 2.499 times 0.08206 times the temperature 273 divided by 1.00. So 2.499 times 0.08206 times the temperature, which is 273, all that divided by 1. So 55.99-ish. We have 2 sig figs from the 110, so my final answer is going to be, 56 liters. How many moles of helium are in a 8.50 liter metal cylinder? It has a specific temperature and pressure. So N is my moles. Volume is 8.50 liters. Pressure is 20.0 atm. Temperature is 295 Kelvin. So PV equals nRT. So we're going to solve for N. Divide both sides by RT. P is 20.0 times 8.50 divided by 0.08206 times 295. That will be my moles. So 20 times 8.50, close parentheses, open, divided by open parentheses, 0.08206 times 295. So I end up with 7.022, what's wrong with me? 5589, all that. So if I look, my sig figs, I have 3 sig figs, so my final answer should be 7.02 moles of helium. Because we're dealing with gases, so I figured it might as well be like gases. Dalton's law of partial pressure states that the total pressure of a gas in a container is the sum of the partial pressures of the individual gases in the container. So this P total equals all of that. That just means if I add up all the pressures, the individual pressures of the different gases, it will equal the total pressure of all the gases added together. So the real life example for this is the Earth's atmosphere. It's a mixture of gases, like we've talked about multiple times. It helps protect us from UV radiation from the sun, warms the surface of our planet by 33 degrees Celsius or 59 degrees Fahrenheit via the greenhouse effect. They kind of insulate the planet and helps prevent differences in temperature that kind of swing back and forth from day to night. So it contains about 78% nitrogen N2 and about 21% oxygen. Argon, CO2 make up other gases, as well as water vapor. You have these small floating particles, if you will, of solids, liquids, and gases. They're called aerosols. That includes dust, spores, pollen, sea salt or sea spray, volcanic ash, smoke, and more. The atmosphere grows thinner as you move away from the Earth's surface. So it becomes so thin that you can kind of tell there's going to be difference in each level of layer of the atmosphere, and different things can occur there. Different temperatures, different pressures, but we'll focus on the things that occur there. So make sure that you are keeping that in mind. So here we have a layered structure. You can kind of see the different layers of the atmosphere as visible. We live in the troposphere. The troposphere is the lowest layer, and that's where clouds and weather mostly occurs. In the troposphere, that's also where we live. Write these down. Next, you have the stratosphere, which includes jet streams, which is where airlines or airplanes travel, and the ozone layer, the protective ozone O3 that helps protect our planet from UV radiation. Also, if you'll notice here, in the troposphere and stratosphere, that's where volcanic ash volcanoes erupt. The smoke end up in both troposphere and the stratosphere. In the mesosphere, we have meteorites. That's where they burn up. The thermosphere, that's the northern lights. And then the exosphere, that's where space is. So make sure you think about what occurs where, because I will ask you about that. So don't be surprised when you see some stuff about that. The last part is standard temperature and pressure. When comparing two volumes of gas, they need to be at the same pressure and the same temperature. Standard temperature and pressure, or STP, 0 degrees Celsius and 273 Kelvin. That's for temperature. Pressure is 1.00 atms or 760 millimeters of mercury. Standard molar volume, so that means in 1 mole of a gas, we have 22.4 liters of that gas. In 1 mole of a gas, we have 22.4 liters of the gas. So what is the volume of 30.8 grams of CO2 at STP? So it tells us we have a standard temperature and pressure of so temperature is going to be 273 Kelvin. The pressure is going to be 1.00 atm. We have a volume that we're trying to find. Notice we have grams, so what can we do with grams? We can convert this over to moles. So it's going to be 30.8 grams divided by 44.01. So 30.8 divided by 44.01, that's going to be 0.699840 whatever. So that's how many moles we have. So PV equals nRT. Notice how it takes different gas laws, but it kind of adds that layer of information. So volume is nRT divided by P. So 0.6998 times 0.08206 times temperature 273 divided by 1.00. Because I'm bringing that up because you're going to see in the next question, it's going to be at STP, but it's not going to be ideal gas law. It's going to be a different one. So 0.6998 times 0.08206 times 273 divided by 1.00. So we have 15.0. I didn't mean to do that at all. 30.8, 3 sig figs. I will change that disgusting number and that answer that you see in front of you. I'll make it right. So 15.7 liters. That's my final answer. Or CO2. What is a sample? The volume of the sample of nitrogen is 6.00 liters. So I have a volume here of 6.00 liters. I have a temperature at 35.0 degrees Celsius. I have a pressure at 740 torr. What volume will this occupy at STP? So my temperature is 273 Kelvin. My pressure is 1.0018. So notice that this is combined gas law, and I know this because it talks about a pressure, a temperature, a volume. I'm trying to solve for volume, but I also have STP. That means I have a temperature 273 Kelvin and a pressure of 1.00 atms. So P1 V1 over T1 equals P2 V2 over T2. But I forgot to do something. I got to convert my Celsius to Kelvin. So 35 plus 273 is 308 Kelvin. I need to convert this over to ATMs. So 1 ATM is 760 torr. So 740 divided by 760, 0.97368. I believe that's what it said. Yep, ATM. So I want to solve for V2. So I'll go over here. P1 V1 T2 equals T1 P2 V2. Solve for V2. Zero point 9.736 times 6.00 times 273 divided by 308 times 1.00 V2. So all that, let's see, times, you able to see this one? Times 6.00 times 273 divided by 308 times 1.00. What was that? So 5.17822. So to make it appropriate amount of sig figs, which was going to be 3. So it's going to be 5.178. So it should be 5.18 liters of N2. All right, that's it for now. If you have any questions, please let me know. Thanks.